Okay. So 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 let me emphasize more on tonight uh, a test, sorry, a quiz. Okay, it will start at 8:15 if I'm not mistaken, 8:15 or 8:20. So please be prepared, at least for the tutorial 1 and tutorial 2. Okay, especially for E22. Okay, you can refer to the Google Classroom where I the recording session of this week's tutorial uh, regarding tutorial 2, part of tutorial 2, especially the earlier part of the tutorial 2. So please, because the quiz will cover from tutorial 1 until first part of the tutorial 2. Okay, so everything will be MCQ. Okay, please answer your questions properly. Okay, you will have, I think, 20 or 20 questions altogether. Maybe questions have not, okay, I'm not sure about that, but okay, just focus on what the MCQ questions, okay. Please, okay, don't get confused between the MCQ questions. There are four, maybe A, B, C, D or A, B, C, D, E, doesn't matter. Okay, don't wait until the last minute to submit your answers. All right. Okay, so let's start the class. uh, the law of motion. So let's do some a bit quick recap on the chapter 4, which is we will learn about the forces. Okay, the Newton's first law, Newton's second law, okay, the Newton's third law, and right now we want to discuss about the applications of the Newton's law until the circular motion. Okay, so when we talk about force, it should be because of the push and pull mode. Our motion in terms of push and pull, where we can actually, because force is a vector quantity, that must have magnitude and direction. Okay, so the Newton's first law is the law of inertia, and object at rest. Okay, an object at rest will remain at rest as long as no net force acting on it, and an object with a constant velocity continues to move with the same velocity. Okay, normally the student only wants to memorize just one definitions of Newton's first law. Okay? But the Newton's first law also can be used to the moving object, like number 2. Okay, we can use Newton's first law to the moving object. Okay? An object moving with a constant velocity will continue to move, okay, with the same velocity as long as no net force acting on it. So that is the Newton's first law. Okay, so the Newton's second law, okay, is about acceleration that is proportional to force. Acceleration to that is proportional to force, like this one. Okay, but inversely proportional to mass. And of course, okay, we can say that F is equivalent to ma. Okay, but normally this is just a normal force equals to ma. But during problems, normally we must put the submission of F equals to ma. So what is submission of F? That means hasil tambah semua force. Okay, hasil tambah. So a summation of F equals to ma can be divided into summation of Fx and also summation of Fy. Okay, so both will be equivalent to ma. Right? So that means when you have a motion that goes left to right, left to right, left to right, for example, you have object that's going to be going to the maybe x, maybe to the negative x. Okay, so it will comply a summation of fx. But when we have for example, in going up y and negative y, then it should follow a summation of fy. This summation of fy. Alright, so okay, so an object has several forces. Actually, the acceleration is due to the net force. So this, okay, this should be the summation of F E M A. Okay, then Newton, or kgms negative 2. Kgms negative 2. Okay, and now we go to the free body diagram again. So what is the free body diagram? Is how you sketch the forces. Okay, how you sketch the forces, isolate the object of interest, choose a convenient coordinate system, and resolve the forces into components. All right. So when we have a forces, for example, okay, for example, at this point, okay, when you have a force, you want to push a sofa, and the sofa of course will have its own weight and a normal force. Okay, weight and a normal force. Remember what force is perpendicular to the surface. Okay, force that is perpendicular to the surface, weight is always pointing downward because weight is equivalent to mg, and normal force is the force that perpendicular to the surface. So all is a forces. Okay, weight, either regardless of the name, is either weight or normal force, is still we noted that as a type of force. So this force, okay, which we call it as the external force. Okay, that is also called force, and we have a normal force. So this is normal. Yes, this is weight. External, weight, or normal, all are forces, type of forces. Okay, so you look carefully. So this should be the free body diagram. Okay, I need all of you, when you try to solve the problem regarding force, make sure, okay, please make sure you use the correct manners, which is when you want to sketch a free body diagram, make sure all the arrows should be pointing outward. Okay, point dia ke luar, ke arah luar. Okay, jangan ada satu pun masuk ke dalam macam ni. So that is not the proper free body diagram. Make sure all the arrows will pointing outward from the system. Let's say this dot is your system. Okay, because that will tell you, okay, how to resolve its component in the correct way. Okay, because we need to resolve every forces in the free body diagram to make sure that we can sum out everything with the proper axis. Okay, according to its own axis. Okay, for example, a normal force. Okay, a normal force in y-axis. Okay, and weight is always in the y-axis also. Weight is definitely always in y, but normal force will depend on the situation. If the sofa is on the floor, okay, that means the normal force is exactly perpendicular to the surface. So that's why we say that when you have a situation where you hang something on the wall, okay, this is the wall. Okay, so this is the weight. Where is the normal force? It should be here. The normal force is pointing to the left because it should be perpendicular to the surface. Okay, so the normal force will keep changing, but the weight is always pointing downwards. Alright, the external force, okay, right now, we have a force that coming into the system, therefore, we can put this, okay, the original one is here, okay, we put this thing to be here, okay, a parallel one, but the arrow is pointing outward from the system. Therefore, we can measure its component f cos theta and negative f sin theta. I hope that everyone have already over in terms of how to resolve a component. What can be done component, either positive or negative. I think that all should be settled by now, right? Okay. So this is the physical free body diagram of a book. Okay, right? Right. We saw this example. Okay, how it affected the F equals to MA. For example, in this case, okay, everybody in the part A is going to the right. Then this is submission of Fx. Okay, and everybody is going Mo is going to the right, Larry and Curly going to the left. Now we also use negative Fx. Submission of Fx means hasil tambah semua force pada arah X. That is so-called submission of Fx. So you need to do something to that value. Okay. For example, in this part, okay, everything is going to the right, therefore you can add it. Okay, tambah saja to get to 124.5 Newton equivalent to A, and then you can find the acceleration. Now, what happens when it encounter a forces that is against the original one? So therefore, we should consider 80.5 as a mole, and negative 80.5, and another negative 80.5 is Larry and Curly. Okay, and therefore you will get negative 80.5. Negative, don't forget the negative, because it should be, our acceleration should be negative. Acceleration of Fx, okay, is equivalent to negative 80.5 Newton. Alright, so then the acceleration should be negative 0.107 meter per second square. Okay, this is another example. Yeah, well, I believe that all of you have already mastered the examples. Right, let's look at the Newton's third law, where every forces that acts on an object, is there a reaction, okay, force acting on a different object that is, okay, equal in magnitude and opposite direction, opposite in direction. Okay, that means the value is the same, but the direction is different. Okay, for example, you can see here when you are pushing a refrigerator, and this man is pushing a refrigerator, you can see this is his force, and then at the same time he's also having a force from the refrigerator. Okay, because he is using some forces to the refrigerator will give some reaction to that force that is equal in the magnitude but different in the direction, because this man is actually pushing to the right, and we can say that the refrigerator is actually giving a force in the opposite way, which is going to the left. Okay, so these are another examples regarding boxes. Okay, please take note on these examples also, because we always tend to believe that a lot of students having a problem when dealing with the examples, especially the Newton's third law regarding boxes. Okay, sometimes it can get you confused, because some boxes, if you add another boxes, for example, box number 3, okay, what happened to the box number 1 and box number 2? All right, definitely box number 1 and box number 2 will have its own action reaction force. Okay, but the 20 Newton here in the examples is where you want to find the where is the external force. Okay, so in this external force, we also considered as F. Okay, but F1 and F2 is considered to be a force. Okay, F2 is the force given to the box number 2, and F1 is the force given by force number 1. Okay, given to the box number 1. Okay, so that is how the symbols of action, reaction. So you cannot, you didn't have to calculate, just calculate one, either F2 or F1, you can get both. Okay, because this is action, reaction time force. Okay, and for example, you can say, if the question wants to ask about, okay, what is the force of contact between the boxes? Okay, force of contact between the boxes, we already have an acceleration in part A. So from the acceleration, and remember, when the object moves together, box number 1 and box number 2 move together, move to the right, let's say, for example, we can consider this one as one acceleration. Okay, we can consider this as one acceleration. So that's the same acceleration for this part. Okay, and then we use the mass that is equivalent to box number 2. This is box number 2, times with the acceleration to get 6.67. Okay, and obviously when so equal to negative 6.67, 7 Newton. Just different in the direction. Okay, so that is the summation of fx, and this one is the example of Jack and Jill, where it emphasizes more. Okay, emphasize more on summation of fy equals to me. Summation of fy equals to me. You can see there a lot of questions. The pill is actually brought up. Okay, the pill is brought up. So this one happens, hey, look carefully, the situation now doesn't involve x. And you can see here, from the summation of fx, okay, normally we put summation of fx equals to ma. But right now we put that fx equals to 0, where? Because of it is equivalent to 0. It doesn't move in the x direction. It doesn't move in the x direction, but it moves in y axis. Okay, y axis. So x direction, okay, it doesn't move. That's why the acceleration, the summation of fx, so therefore summation of fx equals to 0. So that's why when you're dealing with during your high school or your secondary school, okay, you always your teacher always say that this one is summation of fx equals to 0. This one is summation of f equals to ma. Then you get confused because you don't understand the situation. Okay, the situation now is the motion moves in the either x-axis or y-axis. So that based on the acceleration. Acceleration we consider. Okay, if the acceleration is 0, then f equals to 0. Yeah? If the acceleration is given in the if the motion involves x-axis, then f equals to ma for x-axis. Okay, but the main thing you should know that summation of f is equivalent to ma, because this is Newton's second schedule. So when you try to deal with the problem, don't forget about the law of inertia, especially this law. Okay, the Newton's second law. We will use a lot of the Newton's second law inside the problem. Okay, so right now this example is very good when dealing with a situation where Jack and Jill is actually trying to carry up the pail. He carry up the pail, that means the motion is in y-axis. Okay, but because of both have an angle, so therefore we need to do some resolve component. So that's why they resolve in component. Okay, and then it against the y of the from the weight itself, negative 12.8. Okay, calculated, right? And then you tend to get the summation of this one is summation of fy equals to ma. In the end, we want to find what is the summation of fy divided by ma. Okay. All right. Okay, this is another example when you're dealing with the problem. Then for this example, okay, they want to emphasize on what? Okay, if you look carefully, this is about forces. But in the end, they want to ask about if the sled starts at rest, how fast is it going after being pulled for 1.15 seconds? How fast? How fast means they want to find the v, velocity. So velocity, does it involve in the force? Yes. Okay, but we need to see how it relates to the force, because when we try to deal with force, it involves, okay, force involves ma. So this is where you can see how the relations of force that can be discussed through the equations of motion. Okay, from A we can get V, because it's given here the time. Okay, it's given also here in the V naught. So we can use V equals to V naught plus AT. Okay, so this equation, the equations of motion can be used in these types of examples. Okay, maybe we can use that as a V square equals to V naught square plus 2A delta X, for example. Okay, maybe we can use delta X equals to V naught T plus half at squared. Yes, yes, and yes, it can also relate to the equations of motion. When I tell you about equations of motion, then it can also relate if the information is enough. Okay, for example, given to you how many seconds involved. Okay, it starts from rest. All of those things can be used to answer this problem. Okay. Okay, so this is our highlight today. We want to know about the types of other forces. Okay, types of forces, other forces. For example, okay, I have mentioned earlier about weight. Okay, so how can weight can be comparable to force? Okay, it's actually part of the force because when you say the Newton's second law, F equals to ma. Okay, the force is equivalent to the multiplications of mass and acceleration. Okay, multiplications of mass. That means an object that has mass. Okay, an object that has mass with times with its acceleration will give you force. And what happened when the object that has mass that having a acceleration, but its acceleration is has its own name, which is the gravitational acceleration. What can happen? So therefore, they have its own name, which is when mg, it will give you some force. That force W, which means weight. Weight is equivalent to mg, mass times gravity. In this case, g is 9.8. So this is your mass, and this is your gravitational acceleration. To be on precise, is 9.8 meter per second square. Gravitational acceleration 9.8 meter per second square. So the formula for weight is W equals to mg. Okay, but don't get me confused. Sometimes we can also write down as F equals to mg. Yes, why not? Because it's also the type of force. Remember, don't rigid yourself to the force. Okay, it can be called by other names. For example, this one is weight. Okay, now we look at the example. Okay, the fire alarm goes off and a 97-kilogram fireman slides 3 meters down on a pole, down a pole to the ground floor. Okay, suppose the fireman starts from rest, slides with a constant acceleration, is very good indicator, constant acceleration, okay, and reach the ground in 1.2 seconds. Okay, what was the upward force exerted by the pole on the fireman? Okay, so remember, okay, when the fireman, okay, at the fire station maybe, okay, yeah, when they have an emergency, so obviously the fireman doesn't use a ladder. Okay, they always use don't use stairs. Also, they will use they stand to slide using pole. Okay, maybe they have a rest area, okay, or at the upper level, and then they have a fire car, okay, at the ground level. So they will, okay, in order to save time, okay, they need to do very fast. Okay, they just slide them with the pole. Okay, so in this question, they will use about 1.2 seconds to reach to the ground. Okay, so the fireman starts from rest. That means the V naught is 0. Okay, slide with a constant acceleration. So the word constant acceleration is the indicator for us to get to at least note there that we can use equation of motion. Okay, what is equation of motion? That 3 equations that I always tell you again and again. Okay, so when they use a constant acceleration, that is equation of motion. Okay, so what was the upward force? So the free body diagram should be like this. Okay, where the fireman should have a weight here and also the upward force. Okay, this some upward force, maybe sometimes we can call that as a friction. Okay, obviously we want some a little friction when you're sliding down the pole, because if that you can easily get to the ground in very a very short time. Okay, that will give you some. It's very dangerous because of the impact. All right. So we don't want that. We want some upward force. Okay. If you notice here, there are no normal force inside the question because the normal force will take place if there is some surface. So for at this moment, okay, we don't see any surface, so that's why the only weight that can happen to the fireman is the weight. Okay, but it also has an upward force. So now we have upward force and also weight. So we need to know what is our acceleration. We need to calculate the acceleration first because remember submission of F we can only be happen when you have ma. So this is our focus mode should be on summation of F equals to ma. But now we don't have A. How can we get A? We need to use an equation of motion. Okay, we need to use some equation of motion. Either through what? Yes. Okay, well, we can use a lot of ways to find the equations of motion, but this part, okay, because we have y, we have c, and we have v naught, we can use this equation. Okay, normally we just put it as delta y equals to v naught t plus half at squared. Okay, so we can use this one to get a. Okay, this is how they get it. So the answer for A is negative 4.2 meter per second square. Okay, negative 4.2 meter per second square. All right, and then of course, when you're dealing with the F equals, that is acceleration. So right now, they want to know how about the upward force. Okay, the upward force. So how to get the upward force? Yes, first of all, you need to know about F and G. We have a free body diagram of F, the upward force, and also the weight that is going downward. Okay, so in this case, the acceleration, we can calculate the acceleration using here. Okay, the summation of Fy is equivalent to F minus mg. F minus mg. Okay, so that means F minus mg equals to ma. Or can we write down as W minus F equals to ma? Yes. Okay, because it's, the situation now is the fireman is actually going downward at this direction. Okay, so one thing I can assure you that, okay, in either to choose between weight or force, okay, we need to know, okay, the situation. If the situation of the fireman is going upward, then the force will go first, then followed by W. Okay, we can see that the force will reach the top first, followed by W. Ini bahasa senang dia lah, okay. But when the acceleration is going down, that means the motion is going downward. The weight will reach the ground first compared to force, because the weight is actually at the top compared to force at the bottom. The weight is actually at the bottom part, but the force is at the top. So analogy, okay, you use some analogy. Which force should reach the ground first? I believe that everybody should understand why W will reach the ground first, because W is in the bottom part compared to force. Okay, so that's why in this case I'm suggesting you to use W minus mg equals to ma. Okay, W minus mg equals to ma. Then W is equivalent to, okay, ma plus mg, and m equals to a plus g. Okay, and then you put that value, which is negative 4.2 plus with 9.8. Don't use 9.81 like they did, because this is for examples from other books. Then you will find that the F is equivalent to, or the weight, okay. Please note it here. This force, okay, I'm using the weight as a value. Okay, this one is actually weight. This one is force. Okay. Okay, don't get me wrong between that. Okay, so the weight minus F minus mg. So I carry this one as the mg, F is mg. So therefore, weight minus F, okay, you can write down it here, okay, mg minus F, right, equivalent to uh, m equal times with g plus a, then you get 540 Newton. Okay, 540 Newton. Okay, all right. Okay, so now we must see a normal force. Okay, actually, the other name for apparent weight is a normal force. Okay, I should call it as a normal force. Okay, but there's some specific names. Okay, when the object or when the human or when the object is in the elevator. Okay, now we can see that if someone is standing, okay, someone is standing on the elevator, okay, and there is some acceleration. Okay, if there is some acceleration involved, now you can see that there is some weight. Okay, obviously directly, and obviously downward in the downward position. And you can see here there is some apparent weight. Why is apparent weight? Because this weight will depend on the acceleration. With this weight will always will always change from time to time. That apparent weight is actually due to the situation where is the acceleration of the elevator. Either it's going up, okay, or going down. Okay, the elevator can only be up and down. It cannot be left to right. Okay, so therefore we can measure it by using the free body diagram, W and WA. Okay, W and WA. But sometimes I don't want to use it. I always use it as N, normal force, because now elevator must have its own floor. And of course, when a mass, human with some mass is standing on the floor, so regardless of the physical condition is actually moving upward or downward, it must have a normal force. Okay, a normal force can be known also as the apparent weight. So that means you need to measure it, okay, from time to time depending on the situation, because the acceleration can be going upward and can be going downward. That's due to the physical conditions of elevator. Okay, so now we have a weight of this human, and also we have a normal force and acceleration. So how can we write down the equations? Okay, so when the acceleration is going upward, okay, the acceleration is going upward, okay, now we can write down as normal force minus the W equivalent to MA. Okay, normal force minus W equivalent to MA. M is equivalent to MA plus with W, and N equals to MA plus mg, where N equals to A plus G. This is for when the acceleration is going up. Okay, when the acceleration is going up. All right, so let's look at how can we derive the acceleration when it's going down. Okay, it's going down. What happens when the acceleration is going down? Okay, now when A downward, and what happened is W minus N equivalent to MA. N is equivalent to W tolak MA. N equals to mg tolak MA. N equals to G tolak A. Alright. Now you can see both conditions. When an acceleration is upward and acceleration downward. Okay, you can see here the normal force or the apparent weight changing due to the situation. How can I know how to put the W at the in front or W at the back? Okay, so as I said to you, okay, we should consider this. All right, when the acceleration is going upward, Okay, which forces should reach the top first? Okay, where you have a free body diagram like this, which, okay, let's say this is top, this is bottom part. Okay, remember F equals to ma, and F will follow what is the directions of acceleration. Okay, the force will follow because F and A is the directly proportional. So whatever the acceleration of A, the force will follow. Okay, so if the acceleration is going upward, then the force that should reach the top first is W A ataupun N. Okay, so in my case, I'm using WASN, okay, as a normal force, right? So I put it as a normal force. That's why when acceleration is going upward, okay, N, I will use N. I will use N minus W here. N minus W equivalent to MA. Okay, when the acceleration is going downward, then who should reach the bottom first? Okay, I believe that we can agree that W will reach the bottom first. Right? So W will reach the bottom first, and then of course, now this is how I write my equation. W minus N equivalent to MA. Okay, so actually, when I know some of you maybe okay, I don't want to use W minus N minus W. I want to use a different. Okay, I want to just split the same. So for example, everything that goes up must always minus what everything is when it goes down. Okay, forces that's going up will minus the forces that's going down. Forces on the right will minus everything on the left. So when we reach at that level, okay, we should understand this. Okay, for example, okay, let me explain something here. Okay, okay, let's take one example, which is acceleration downward. Okay, for those what I'm teaching you here is based on the condition, which means which force should reach the bottom first when the acceleration downward. So therefore, in my case, W minus N equals to MA. Okay, and then we can get N equals to W minus MA. Then W is mg minus MA and equivalent to G minus A. So that is one condition. What happens if I don't want to use W minus N, but I still believe that everything that goes up must minus what everything that goes down. Okay, so saya selalu kalau orang yang nak macam tu, dia selalu yang belah atas mesti tolak yang belah bawah, yang belah kanan mesti tolak yang belah kiri. Dia memang stick pada benda tu. Dia nak yang macam tu je. Okay, so what happens is, yes, you can always use that thing. Okay, for example, you want to put N at the in front. Okay, no problem. N minus W because N is on the upward force and W is on the bottom force, downward force, is equivalent to, okay, this time, remember, N minus W is actually going up, okay, but the acceleration from at this scenario is actually going down. So you need to put negative MA. You need to put a negative MA because N doesn't follow the acceleration. Okay, N that you put in front doesn't follow the acceleration. So therefore, N is equal minus W equals to MA. What happened? Okay, now look. So N equivalent to, okay, W minus MA. Okay, because I brought this here, and N will equal to mg minus MA, and N will equivalent to G tolak A. Now you can see it's all similar. Okay, because we don't want any confusion. That's why I'm saying you, because because here we want to practice this thing, and before we come to the situation where you have a pulley system afterwards. Okay, a pulley system afterwards will give you much more clearer visions regarding this thing. Okay, all right. So this is a normal force, okay, that is also related to upward force, and the normal force is always perpendicular to the surface. Okay, so look at this physical picture of the person, okay, try to give some force, try to push his back, okay, push his or her back, okay, that her back is actually on the floor, okay, it's actually on the floor. So therefore we have a force, okay, force, and we have a weight and a normal force. Okay, weight because it has mass, and normal force because it is on the perpendicular, it is on the floor. This bag is on the floor. Okay, so then you need to take out all the forces, and then of course we need to bring it like this, from this to this. This is what we call a free body diagram. Okay, try to practice this free body diagram whichever you are trying to solve the problem, because the free body diagram will give you some clearer version. Okay, give you a very good a practice to solve any problems regarding force. Okay, because we noted here, okay, when you're dealing with W, okay, it doesn't have an x-axis, it must have a y-axis, because the W or weight is always pointing out downward. It's always pointing downward, straight downward. It doesn't bend to a certain angle. No, it doesn't have a bending of certain angle. It's straight downward, and normal force will be always perpendicular to the surface. Always perpendicular to the surface. And then we can add another external force here, which means in this external force it also includes with the angle. Then it comes with the component F sine theta and F cos theta. How to write down it as a let's say the acceleration is going that way. Okay, how to write that as acceleration? Okay, in this case we need to remember that this bag, okay, regardless of how you want to pull it, okay, it will always move, okay, on the floor. The gerakan dia mesti duduk di atas lantai sahaja. Tak adalah kata dia tarik bag ni melayang ke atas macam tu. Okay, dia tak melayang ke atas. Kan, tak ada pun dia melayang macam ni. Tak. Okay, you tarik dekat sini, okay, you will be pulling this bag, and it will always move along x-axis. Along x-axis and not in y-axis. So therefore we need to establish the summation of fx, okay, equal to ma, and another one is summation of fy ma. But in this case, you can see here there are no motions of the bag, okay, in terms of y-axis, because the bag move only along x-axis. Okay, it doesn't float. Dia tidak terapung ke atas. Okay, dia tak naik ke atas pun. Therefore, we can say that acceleration in y is 0, so summation of y is equivalent to 0. Now we can understand. Afterwards, you don't have to put this one. You already established. The main thing in physics is summation of fx equals to 0, summation of fy equals to ma, and summation of fy equals to 0. This is physics. Okay, whatever you do afterwards is just a matter of mathematics, like calculating things, so on. Okay, so the main thing about physics is summation of fx equals to ma, and summation of fy equals to 0. So in this case, we need to separate everything, which is whatever happens in fx. Okay, so we can see here there are only one forces involved, which is f cos theta equivalent to ma. So f is equivalent to ma over cos theta. That's fine. All right, so let's look at what happened to the y. What happened to the y? So summation of fy equals to 0. So what happens on the y? So when fy equals to 0, that means it doesn't move in y-axis. So we can put either one. We can put everything at the top minus everything at the bottom. So at the top is we have n here. We have n plus with, okay, plus with f sine theta, because f sine theta is also pointing upward. F sine theta. Okay. Now we don't have any more. Minus with w equivalent to 0. So let me write down first. We have n minus plus a f sine theta minus w equivalent to 0. So that's how you write down its equation. From this, you can either get it the acceleration, okay, maybe you can get the normal force, but this is the fundamental of how you can write down the equations, and this is very crucial part. Okay, please, okay, spend some time learning how to get to know that equation, how to get to use okay, from this free body diagram, I can write down that some equations. From this diagram, I can write down some equations. So if you are able to write down the equations according to the free body diagram, then everything's solved. Okay, you don't have to worry. Any questions, a piece of matter. Okay, senang. Tak ada masalah dah lepas tu. Okay, but you need to know how to write down some equations involved when you have a free body diagram. One thing, okay, sketching a free body diagram is a very good method, okay, to get to know the forces. Okay, so when you have a problem regarding forces, make sure draw some free body diagram. It doesn't, the question doesn't ask you to draw. Obviously, it doesn't have a mark of drawing, but sometimes they can put it inside the question. They can put it. Sketch the free body diagram regarding da. Okay, but okay, please, okay, just a practice of yourself. Okay, practice in order for you to get or to familiarize yourself with the situations of forces involving Newton's second law. Okay, right. So these are some applications of the Newton's law. For example, we have a tension. Okay, what is tension? Like this. So this is some tension. Okay, why they use tension? Tension is also a force. Okay, don't get me wrong. Don't confuse between what is tension. Tension is also a force. Okay, tegangan. Okay, also a force because it also applies some pull and push to the system. Okay, for example, when we hang something, kita gantung satu barang, then we can see there's some tension. Using a string, for example, a simple string, we can obviously say that we have a tension. Okay, tension is very important to understand when you deal with tension. Okay, obviously, the forces will be applied to this four, at least four of this situation where you can have a tension. We can have an inclined system. We have an elevator, for example, elevators and a pulley system. Okay, you can see the force in terms of these four applications. Okay, so number one is tension. Let's look at whatever happens in tension. Now, for example, okay, a traffic light weighing 100 Newton. Okay, so that means this is the W. It's also called force. Hangs. Okay, hangs from a vertical cable tied to two other cables. Vertical cable tied to two other cables that are fastened to a support. As in figure A. The upper cable makes an angle of 37 degrees and 52 degrees with the horizontal. Okay. Find the tension in each of three cables. Now you have three cables. Okay. For example, this situation. Okay, this situation I will use this part because it's quite clear over here. Okay. You have a system of traffic light. Okay. Don't bother about traffic light. So you will have some strings and it's connected between two things. Like this. Okay. And it's been connected to a wall. So this one is 37. This one is 54. Okay. Well, what is the connection between all these things? Okay. When you deal with tension, okay, obviously you will be given a cable or a string to connect. Okay, connect the systems to the wall. Okay, whatever happens to the wall, okay, remember, okay, the wall is very, very firm. The wall is very, very precise. The wall is sangat kukuh di atas tu. Okay, so therefore, we have a string or that attached to the wall. Okay, know the direction. Number one is the important thing when you deal with the tension is the direction of tension. Very important. Students set of good directions of the tension. Okay, so the directions of the tension should be the very firm, the very firm scenarios. Okay, for this, yes, like that. Okay, so we can put it here as T1, T2, or whatever the name you want to use. Now, between the cable and the wall is done. Okay, so number two is we should consider the uh, situation here. Okay, the situation here, now, whatever happens to the string system, okay, when you have a string system like this, remember, okay, the concepts of force that can involve between the strings is actually the force or the directions of tension should be against each other. Yes, the tension should be against each other. Okay, so meaning that you will have the same tension. This one will apply in the Newton's third law. Okay, you will have the same action acting on the other one, and the other one will give some reactions that is equivalent to that tension also. So in this case, okay, this traffic light is connected to the cable, so therefore you can have a T3, and another one is T3 is going here. Okay, so that means I can redraw back like one like this. This is T1, T2, and T3. Okay, and of course this T3 will always have T3, and now you draw, and because of this one has mass, so it will have its own energy. So there are certain things you should reconsider. Okay, the first thing is you need to know about 37 degree, 54 degree, okay, and about T3 and about this is when you when you sketch the situation, it is good to know the directions of tension. Why? Because we want to establish, uh, we want to find, obviously we want to find the T1. What is T1? What is T2? And what is T3? At least we have three different unknowns. Okay, we want to find what is T1, T2, and also T3. Three different unknowns. Okay, in mathematics, when you have three different unknowns, the least equation that you must obtain, or you must write down the least equation, you must at least have three equations at least. You need to write down at least three equations. The number of unknowns should be equal or greater. The number of equations should be equals or greater than the unknown. If you have three equations, you must at least have three equations. Can you solve the three unknowns using two equations? No. Can you solve three unknowns using one equation? Definitely no. But can you solve three unknowns using six equations? Yes, because it's greater than the value. So that is something that you need to remember. T1, T2, T3, three unknowns. So at least you must write down three equations. So how to write down three equations? You need to draw a free body diagram like this. So this is how they get it. Okay, so for example, this is T1. Okay, because it's obviously 37, so zigzag. Okay, angle zigzag is 53. Or I'm sorry, this one should be 50, not 54, 53. Okay, so it's written here 53. So this is how they write down 53. Why they need to know the angle? Because they want to break it into or to resolve it into its own component. For example, T1, they have a negative T1 cos 37. Why is negative? Why is negative? Because it's in the second quadrant and because of it's going this one. This one is negative T1 cos 37. Look at how they write down. Yeah? And of course, Ty is T1 sine 37. Positive value. Okay. Why is T2 cos 53? T2 cos 53 is here. T2 cos 53 and this one. Okay. Along the y-axis is also T2 sine 53. T2 sine 53. Okay. How about T3? T3 is on the downward position. T3 is on downward, therefore it doesn't have x-axis 0, but it have a 100 Newton weight, and of course that is in y component. And then you add up to everything. So this one should be in the summation of fx, and this one is summation of fy. You can see here, this one plus this one equals to 0. Everything on the y component is added to be 0. Why? Okay, it's simple. Okay, because we need to know that everybody summation of fx in this question is equivalent to 0, and summation of fy in this question also equals to 0. Why? Because the traffic light doesn't move, okay, left to right, up and down. It doesn't move that way. Doesn't, okay, because the traffic light is a static moment. It's a static thing. Dia duduk diam je. Traffic light tu tak bergerak kiri, kanan, atas, bawah. Tidak. So therefore, everything will be equivalent to 0. So that is how we resolve it. This all the physics, and then the rest of it will be is based on your mathematics and how to get to the second parameters, T2, the third parameters. Okay, you want to do it simultaneously. This is what we call a simultaneous equations, right? Okay, T1, you have T1, T2, and T3 simultaneous equations. Then you need to establish all these equations. Okay, for example, now we have T2. Yeah, when you calculate it, you obtain T1 first, and then afterwards you calculate T2, and then you get to the T3, for example. Okay, and obviously T3 is 100 Newton. Okay, so this is very good questions or examples you can easily refer to. Okay, maybe we take a break for a while. Do you have a question to ask? Okay, Alhamdulillah, so far so good. Okay, so let's continue on the frictionless, on the flat on the frictionless hill. Okay, so we try to continue. We will try to discuss about application of forces. Okay, obviously we have to discuss it through examples. All right. So this look at these examples, very good examples. A sled is tied to a tree on the frictionless, okay, a frictionless snow-covered hill, as shown in figure 4.15. If the sled weighs 77 Newton, find the magnitude of the tension force T exerted by the rope on the sled and that of the normal force N exerted by the heel on the sled. So that means they want two things. First is to get the tension T, okay, and number two is a normal force exerted by heel on the sled. Okay, so this is sled. This situation is actually involve two applications altogether. Okay, because it also it's just not just it's not just uh, um, friction. Okay, actually three. Yeah, it's just not an inclined situation. Okay, an inclined situation, but it also involves. Okay, it also involves uh, tension. Okay, it also involves tension. So we can say that the sled currently, by looking at the situation, the sled is not moving because it was tied to a tree. So that means the tree is very firm. Okay, so we can write down that this sled should have a tension to that tree. Tension to that tree. Okay, then our job is to find what is the tension and also the normal force. Okay, so in the inclined situation, you need to know something. Okay, so let's do something about. Okay, in inclined situations, we need to establish some ground rules. Okay, so for example, now we have let's see another color. Okay, let's say this is your incline. Okay, so this will be your incline. Okay, and then you may have a box here, for example. Okay, all right. So right now our job is to find the free body diagram for this force. Okay, free body diagram. Normally, the one thing that we can understand, or one thing for sure that we can write down is number one is here. It should be straight downwards. That is W. Straight downwards. And then because of the inclined situation, another force that could be established is the normal force. Okay, a normal force that is here. Why? The normal force is not parallel to the W right now because it's due to the perpendicular to the surface. Normal force is perpendicular to the surface. Now we can jot down as here. Okay, so we can say that the normal force is actually straight like that way. Okay, and then you need to do some here, something like this. Okay, okay, so just do it like that so that you will really know. Okay, that W itself. Okay, W itself. Okay, because maybe due to let's say give some angle 30 degree. Okay, maybe incline at the 30 degree. So you need to do some resolve here. Okay, for example, this 30 degrees will give you this part. Okay, this angle of 30 degree is actually here. 30 degree. Duduknya di situ. How do I know? I just expand this thing. Okay, saya expand saja. So kalau dekat sini 30. Okay, so dekat sini akan jadi 60. Dekat sini jadi 90. Simple. So kalau dalam yang ni, dekat sini 90. So dekat sini pula akan jadi 60. 60. Each one akan jadi, yang dekat bawah tu 90. Sini akan jadi 30. Right? Simple triangular solution to get to know that that one is the 30 degrees. But if you, for those who want to memorize, just memorize this 30 degree is equivalent to this part. Okay, between the weight and also the y component of n. And we obviously want to apply that the situation now has been different. Okay, the Cartesian coordinate has become like this, x and y. Okay, it doesn't like a normal one. Okay, but okay, now we have w at a certain angle, so you need to do some. W is mg, definitely is mg. W equals to mg. So we need to write down the equation of this. This one is mg cos theta. Okay, because and this one is mg sin theta. Okay, mg sin theta, mg cos theta. Theta is 30. Okay, due to this part. Okay, so right now you need to know. Okay, normal mg sin theta, mg cos theta. So this is the basic of the force acting on the object that is in an inclined situation. Okay, so let's look at the situation of this. Okay, the difference between what I have tell you afterward just now is that this part, okay, this lead, okay, involve a tension. Okay, so when this lead involve a tension, then we need to add a tension. So first of all, okay, we need to draw W, or just write down as mg. Okay, this one is the mg. Okay, where is the normal force? Here. This is the normal force. This one is the tension. You can draw it like that. Okay, and therefore, what is this? This is 30 degree. This one is mg cos theta. And going back, here is mg sin theta. Now we have already established all the forces involved in this situation. Okay, and so in this situation, now we have Cartesian coordinates like this: x going to that way, y is going to that way. Okay, so if you look carefully at the one that they did here, okay, they put here as negative. Okay, negative. But don't bother to put that, because that is just as simple as whatever to the left is going to be negative, whatever going down is going to be negative. Simple. Okay, so don't memorize all those things. Okay, so look carefully. We want to know, we want to measure the T, the tension, which is here, the tension, and we want to also to know about normal force. So right now we can establish that the T is in x-axis and n is in the y-axis. Yes. Okay, so when we're dealing with T, okay, let's look at here, T first. Okay, now we have T at the x-axis, we have T and we have mg sin theta. So how to write it down? So now we can write it as summation of fx equals to 0. Okay, because everything is not moving, x-axis doesn't move, or y also doesn't move. So we can write down it as T minus with mg sin theta equivalent to 0, T equals to mg sin theta. Okay, T equivalent to mg sin theta. What's the value of T? Okay, by using m, okay, because m times g is already 77. Okay, sin theta, sin 30. Now you will get 38.5 Newton. The answer for T is 38.5 Newton. Okay, now it's done for the tension. And how to get n? N is in the y-axis. So you need to establish a y-axis. So again, summation of Fy equals to 0. So what happens here? We have n and we have mg cos theta. So n minus mg cos theta equals to 0, n equals to mg cos theta, w cos theta. So in the end, we will get the value is 66.7 Newton. Okay, so that's how they calculated using inclined situation. Okay, let's look at another part of the inclined situations using a car. Okay, for example, this way, the runway car. Okay, it's not tied to any tension, so this is very good example because it's quite different from the previous one. Okay, a car of mass m is on an IC driveway, inclined at an angle of 20 degrees is in figure. Okay, so determine the acceleration of the car assuming the incline is frictionless. Again, they mention frictionless. That means we don't have to consider a frictionless. Okay, right. So first of all, we need to do some sketching. Okay, again, use look at how they write down. Okay, this is the car as a dotted line. So this is the W. Alright, because it's going this way. Remember, so this is the 20 incline. 20 is equivalent to 20 degrees. So happen to be here. Okay, 20 degrees. Now we have mg sine 20 over here, and obviously mg cos 20 at the bottom. Okay, because that is how you resolve W. Okay, and obviously there is some and a normal force. You can write down it like this. Okay. Okay, so the question now is find the car's acceleration. Okay, the car's acceleration. So by our judgment, the acceleration is based on the car. The car is moving on the x-axis. That way. Okay, so the acceleration is going down. Therefore, we can put it as summation of fx equals to ma. Just now, we put that as the summation of fx equals to 0. Why? Because acceleration 0. Okay, the sled is not moving. But right now, the car is moving. So therefore, the fx equals to ma. Okay, the fx equals to ma. But it's in fx. Now we have mg sine 20. So we put that as mg sine 20 equivalent to ma. Now you can cancel out m. So g sine 20 equals to a. A is equivalent to 3.35 meter per second squared. Okay, you can try it out, right? Okay, so that is acceleration. The part B is the length of the driveway is 25 meters and the car starts from rest. Okay, so this one is x, this one is v0. At the top, how long does it take? How long does it take? So they want to find t. Okay, so meaning that delta x equals to x naught plus v naught t plus half a t squared. Okay, this one starts at 0, this one also 0. So now we can replace the acceleration to this part. Okay, and then we may find what is the t, and the driveway is 25. So the answer for t is 3.86 seconds. And then what is the car speed at the bottom? The car speed. So the car speed we need to establish it using v equals to v naught plus at. So v naught is 0. Now a is 3.35 times with 3.86. Now you will get the value is 12.9 meter per second. Okay, that's how they can relate from one problem, which means that we want to find the acceleration from the our judgment in terms of force. Then we can relate to the equations of motion. Remember, when we deal with the force, make sure you know about the motion. Okay, let's look at another situation of force, which means the elevator. Okay, a woman wakes a fish with a spring scale attached to the ceiling of the elevator. Okay, as shown in figures 4.19 and 4.19b, 19ba and 19b. While the elevator is at rest, she measures a weight of 40 newton. So when acceleration is 0, the weight is 40 newton. So which means the weight of the fish is 40 newton. Okay, what weight, number A, what weight does the scale read if the elevator accelerates upward at 2 meter per second? Accelerates upward at 2 meter per second. So how going to do the problem? Okay, so first of all, you need to establish these things. Okay, the submission of fx will be 0 because there is no movement in A, acceleration in x axis, but we need to know the fy will be equivalent to ma. So this is how you need to write down it first. Okay, the situation fy equals to fx 0, fy equals to. Sometimes just by writing it down, you may get the mark. Okay, sometimes, alright. So summation of fy equals to ma. So you need to know what is in fy. So if the situation is the elevator is going upward, okay, what happens when the elevator going upward? Okay, definitely you will have a tension. Okay, and maybe a normal force going because there is how they did they write down it as a tension. Okay, so the weight, because they want to know about the weight of the scale rate. Okay, the scale is hanging by using tension, and obviously they have an mg. So T minus mg equals to ma. So T is equivalent to ma plus base mg. How do I know to put T or mg at the front? Like I'm saying just now, okay, it will follow based on acceleration. My acceleration is going upward, then who should read the top first? Definitely T. T akan sampai dulu berbanding G. Okay, so berbanding mg. So T duduk di depan, T minus mg equals to ma. T jadi semua bawa ke sebelah sana equals to ma plus mg. Then you can this one to get T is equivalent to ma plus g. And then you will get to the answer is 48.1 Newton. Write the correct unit. Okay. Alright, whatever happens when at part B, what does the scale read if the elevator accelerates downward? Accelerates downward at 2 meters per second. Okay. So right now you have mg going downward and you have T going upward. Okay. So who should read the bottom first? Now you should read you should draw it as mg minus T equivalent to ma. So what is T? T is equivalent to mg minus ma. So what is T minus ma? G tolak A. M is 40 for 9.8 minus with A is 2 meters. So you will get to know that the answer will be 31.8 Newton. 31.8 Newton. Okay, G is 9.8 and A is 2. A is 2. But it's going downward. So the answer is 38.1 Newton for the B part, and the C part, the A part, you will get 48.1. Okay, and part C, if the elevator cable breaks, what does the scale read? What does the scale will read? So based on this, on our term, the scale will read at this one. Okay, the acceleration right now will become the same acceleration. Okay, acceleration at this part will be equivalent to negative g, which is negative 9.8 meter per second. Now you get you times with the positive 9.8, so it will cancel everything to get 0. And then there are no tension because there are no break. Okay, the tension breaks, no tension becomes 0. Okay, now we move to pulley. Okay, two objects of mass m1 and m2 with m1 is greater than m2. Sorry, m2 is greater than m1 are connected by a light extensible cord and hung over a frictionless pulley. Okay, as in figures. Okay, there are two things you need to remember because in this case we are having a pulley. This pulley should be what? Okay, it should be light. Ingat frictionless. Frictionless, and also the cord. Okay, tali tu must be light, extensible or inextensible. Tak boleh direnggangkan. Tak boleh ditarik. Maksudnya kan ada setengah tali yang dia boleh direnggangkan. Okay. So inextensible maksud dia tidak boleh direnggangkan. Very light macam benang lah contoh dia. Ada syarat-syarat dia. Sebab in the next chapter afterwards nanti kita akan belajar mengenai kita akan belajar another topic yang ada pulley balik. That pulley masa tu mesti dia berbeza dengan pulley yang kamu belajar sekarang. Okay, so adalah benda-benda yang we need to assume that the pulley is light and frictionless. Mesti frictionless. Kalau pulley itu ada friction, then we need to consider the friction. Okay, and the pulley must be light, mesti ringan. Pulley itu mesti ringan. Okay, so that's the cord. Okay, both cord and pulley have negligible mass. Find the magnitude of the accelerations of the system and the tensions in the cord. Okay, bila you tarik, bayangkan situation dia, bila you tarik M2, okay, bila tarik M2, ini ialah tali yang sama, tali yang sama. Obviously, there are two accelerations involved. Okay, ada satu acceleration, ada seolah dua situation. Tapi hanya ada satu acceleration. Number one, acceleration on this part, acceleration going upward, and this part, acceleration going downward. So in order to do that, so you need to break these two situations. Contoh dia, this one is M1, katalah M1 sini, acceleration going that way. So dia ada tali ke atas. Okay, tali dia ni ada some T tension, dan dia punya bawah ni ialah M1G. That means dia punya weight. Okay, ini yang pertama. Yang kedua, dia akan ada satu lagi, which is M2. Dia akan ada M2G dan dia akan ada tension ke atas. Acceleration ke bawah. How to write the correct equation when dealing with this problem. Okay, so pada masa ini, okay, when this problem happens, okay, you look at the situation. Okay, untuk acceleration naik ke atas, siapa yang duduk di hadapan? T berbanding M1G. So dekat sini kita akan tulis dia as this one. Okay, the equation for this part dia akan jadi T minus M1G equals to M1A. So that is number one equation. Okay, for this part, for the second part, dia akan jadi macam mana? Dia akan jadi M2G tolak T equivalent to M2A. Because based on our submission of F equals to MA. Yang ni bersama. Submission of F equals to MA. Tapi tengok, how do I write it? Okay, T minus M1G, M2G minus T. How do I write it? Yes, based on the directions of acceleration. Based on the directions of acceleration. For example, situation number one, Acceleration is going upward, naik ke atas. Siapa yang akan sampai dulu? T dulu sampai, baru M1G. Itu maksud saya. Maksudnya siapa force yang duduk di depan? T. Kalau untuk sampai ke bawah, yang di sebelah dua, okay, situation number 2, okay, the acceleration going downward, who will reach the ground first? M2G akan sampai dulu berbanding T, sebab T duduk di atas. So therefore, that's how I know how to write down the equation. Simple, right? And then, of course, you can do some simultaneous equation from these both equations. Okay, because in order to solve the problems of tension or acceleration, we need to establish at least 2 equations. Kalau ada 2 unknown, 2 equation ataupun lebih. Okay, kalau ada 3 unknown, maksudnya kena 3 equations ataupun lebih. Boleh tak kalau 2 unknowns, 2 equations? Boleh. 1 equation? Tak boleh. Okay, mesti sama ataupun lebih. Right. So let's move to another part, which is the forces of friction. Another type of force that you should consider when you trying to understand the applications of force. Okay. This is the applications of force that I'm talking, which is the applications of Newton's law. Okay, we have already discussed about all of these examples, but this one we want to furthermore in terms of FK. Okay, kinetic friction and also a static friction. Okay, kinetic friction or static friction. So what is kinetic friction or static friction? Okay, let's look at this example. Okay, for small applied force, the magnitude of the force of static friction equals the magnitude of the applied force. Okay, the correct word is friction happens regardless of the situation. Either it is in moving, it's in motion, or it's in a static condition. Okay, kedua-duanya ada friction, kedua-duanya ada geseran. Right? So please note it here. Okay, jangan salah faham. The friction is always occurs to the any conditions, either friction, either in motion, okay, that means moving, or not moving, static, okay, not moving or static. Both, okay, can absorb, can have a friction, but what condition is if our force doesn't have friction during if it's stated in the question, assume the slide is frictionless. That means no friction. So therefore we can find that only that time there are no frictions. But if not stated, maybe using surface, maybe they call it as a rough surface, all of that will contain friction. Okay, will contain friction. Okay, for small applied forces, the magnitude of the force of a static friction equals to the magnitude of the applied force. Okay, look at the applied force. This is the applied force. So the direction of the static friction is going to be against the direction of applied force, like this one. This is the direction of static friction. So this is the static friction. It should be against the directions of force. If you look at the kinetic friction, okay, static when the object is not moving, but when the object moves, when the magnitude of the applied force exceeds the magnitude of the maximum force of static friction, the trash can break free and accelerate to the right. That means when it reach the applied force greater, okay, applied force greater than the Fs, then it will move. Okay, but if F equal to Fs, not move, static. Okay, simple one. So, what is the static friction? The static frictional force keeps an object from starting to move when a force is applied. Kan bila kita nak tarik something kan, dia macam nak gerak. You try to imagine when you try to push something on the rough surface, for example. Mula-mula tu rasa macam susah. Lepas tu lama-lama once dia dah gerak, okay, dia senang je nak gerak. Okay, and then so the equation for the static friction will be mu Fs equals to mu s kali dengan not this one Fs is equivalent to mu s kali dengan n. What is n? Normal force. Okay. What is mu? Mu is the coefficient of, if mu s, static friction. Okay, mu s is a given. Okay, mu s has its own value. For example, this is mu s. Steel on steel, aluminum on steel, so this is mu s. So you don't have to memorize all of the value because it should be given in the question. So maybe they want you to find the mu s. Okay, so you can see here a lot of a surface that give us certain value. But the smallest one will be when you look at the value, a very small value, okay, will influence the how rough is the surface. Okay, the smaller the value, that means the surface is slippery. Okay, all right. So this is the kinetic friction. The friction experienced by surface sliding against one another. If velocity is constant, and happens to be, again, okay, the equation is Fk, is the mu k times with n. Mu k times n. N is the normal force. Again, okay, for the friction, the one thing that can influence the friction is just a coefficient of kinetic friction and a normal force. Yes, a normal force. Okay, friction always occur in the beauty of friction is friction always occur in the directions of applied force. For example, this applied force is going to the right. We know that the friction will take place on the left. But what can influence friction is not something bordering in the x-axis. Okay, but according to the equation, Fk is equivalent to mu k times n. What is n? So according to our situation, the n will become n minus mg equals to 0. So n is equivalent to mg. So regardless of the situation, the direction of force, we actually try to understand friction, but because of the friction will be involved, okay, the friction will involve x and y altogether. So you don't need to know if the friction doesn't include in your situation or the problem where you need to calculate it from the from scratch. You need to calculate it from scratch. Then you need to consider x and y axis altogether, because you cannot get friction but just by considering x axis only. Okay, you need to establish, you need to know, because based on the equation, Fk is equivalent to mu k times n. It involves normal force, and you know when it involves normal force, it involves a surface. Surface normally in y axis. So that's why it's very good to understand the friction, because the friction is moving in x, but it depending on some things that moving in y. So we can get both concepts of x and y all together by learning friction. That's why we put friction at the back of the application, at the last part of the application. Because when you try to understand the applications before this, maybe due to tension, due to inclined situations, maybe due to the elevator or some pulley, all involve very straightforward, maybe x-axis or y-axis. Sometimes we can do both, but for the friction, yes, it always involves x and y all together. Okay, all right. So these are the some value of the mu s and also mu k. As you can see here, the value of mu s is higher than, obviously higher than the mu k. Due to what? Because it is the force that try to dam the motion. Okay, untuk memperlahankan pergerakan yang baru nak bergerak. Bila dah bergerak, dia akan lagi senang. Okay, simple. Okay, mu s yang paling kuat ni value dia. If you look carefully at the situation here, you can see this is where you get the static region. Okay, you believe that, okay, as it try to move, the force becomes increase at certain level, increase, and it reach at the highest peak of the static region, and then afterward it will decline to be on the just a kinetic region. So first of all, the static region will increase, at least reach at the maximum point. Okay, maximum point, and then it will be decline to be on the kinetic region. And if you look carefully at Fk, the value of Fk is obviously lower than the value of the Fs. Now we look at the examples here. Okay, very good example. Suppose a block with a mass of 2.5 kilograms is resting on a ramp. If the coefficient of static friction, now look at how they write down. If the coefficient of the static friction between the block and the ramp is 3.5, so this one is the mu s, 0.35 Newton. Mu s doesn't have unit because it is a coefficient. What maximum angle can the ramp make with the horizontal before the block starts to slip down? So as usual, okay, you need to establish mg. So this one is mg. Now we have mg sin theta over here. We have mg cos theta over here. We have normal force, and at this time, okay, because the questions include coefficients of static friction, so we can put it, because we know this box will go down a certain acceleration. So this is the motions of the box. So the friction, the directions of friction is against the motion. So it should be going the other way around. Now we have Fs, mg sin theta, mg cos theta, and normal force. Okay, so you need to establish two things. Okay, first of all, summation of Fx equals to ma, and another one is summation of Fy equals to 0. Okay, Fx equals to ma and Fy equals to 0. But in this part, okay, what maximum angle can the ramp make with the horizontal before the block starts to slip down? So therefore, in this part, acceleration also 0. So the Fx will become 0. Okay, so in this case, we can define what is mg sin theta. Remember, mg sin theta minus mu sn. Okay, this is the Fs. Okay, the mg sin theta minus mu sn. So they don't want to use And then of course we believe that mu Sn is mu Smg. Okay, so the Fy is in the n minus mg cos theta. So n equals to mg cos theta. Okay, we bring this thing to the right side, and then we put the mg cos theta into the equation number 1. Okay, so then we can get theta equivalent to 19.3 degree. Okay, so this is how you get to the examples. Okay, let's look at another example. The hockey puck in figures struck by a hockey stick is given an initial speed of 20 meters per second on a frozen pond. The puck remains on the ice and slides with the 120 Newton speed, slowing down steadily until it comes to rest. Determine the coefficient of kinetic friction between the pucks. Okay, so they need to know what is the mu k. So first of all, you need to know the acceleration. Okay, the acceleration using v square equals to v naught square plus 2a delta x, where you can find the acceleration from the given displacement. So the acceleration to be 1.67 meter per second square. Okay, and then you can establish that this is the normal force mg. Okay, and the part is going to that way, and obviously it will have a certain friction. Okay, the kinetic friction. So what happens in the Fy is n minus mg, and n is equivalent to mg, and in x is just only fk. Okay, so negative fk equals to ma. What is negative fk? Negative mu k with mg, because n equals to mg equals to ma. Now you can cancel out m, and in the end you will need to find what is mu. So the mu will be equals to 0.170 value. Okay, because it doesn't have unit. Okay, so look at another example. A block with mass m1 4 kg and a ball with mass m2 7 kg are connected by a light string. And look at it, they use light string that passes over a frictionless pulley. This is a very good indicator of what I'm just saying now. Okay, as shown, the coefficient of kinetic friction between the block and the surface is 0.3. The coefficient of kinetic friction, so mu k is 0.3. Find the accelerations of the two objects. Okay, and tension in the string. Okay, remember tension in the string, you should write down as T and also T. This is the acceleration going down. This one they have m2g, this one they will have m1g. Okay, all right, so how to write it down? Okay, it's based on the two situations here. First is whatever happens on the table, and another one is whatever happens when it's sliding down. So there are two possible situations here. Now we have first of all here, look at this part, T minus Fk. Okay, because you have mu k. Okay, the friction between the boxes and also the surface of the table. So this should be the directions of Fk. So T minus Fk equals to m1a. Okay, m1a. So what is Fy on this part? Okay, so meaning that this part it also have x and y, and this part also have just y axis. Okay, so this is for box number 1, and this one is box number 2 separately. So they calculate the equation from equation number 1. Okay, now you calculate the second boxes to get the second equation, and then they jumble up everything in order to get to the acceleration, because in equation number 1 it also has a1, and equation number 2 also has a1, so you can replace this a1 inside this. So therefore the a1 will become 5.17 meter per second square, and replace the value of a1 inside each equation. Any equations of maybe equation number 1 or equation number 2, you will get to 32.4 Newton. Okay. The last question is check the answer for the acceleration by using the system approach. System approach. So you are using another type of acceleration. Okay. The acceleration they considered, or they can use using the first one, that's the acceleration. So this one is get 32.4 is based on equation number 1. Then try to get the acceleration using equation number 2. Okay, simple. We can also get acceleration is equivalent to 5.17 and tension equivalent to 32.4 Newton. Remember, Fk is mu k times n, Fs is mu s times n is the normal force. Okay, so I assume this one is we already set. We already discussed about what is the direction, which is the direction of the tension. And then it goes back to the Hooke's law. Okay, using spring F equivalent to negative kx, where F is the applied force, K is the spring constant, and X is the elongation. Okay, spring constant and elongation. F equals to negative kx. Okay, so stated here, translational equilibrium, okay, is based on the situation. Either it has acceleration or it doesn't move. The connected object. This is what we have discussed earlier part. And the last part, okay, I will leave this part, the circular motions, on Friday. Okay, we will discuss it on Friday about the circular motion. Okay. All right. So, any questions so far? Basically, there are these 4 equations. So, kalau include friction, just tolak daripada mg sin theta. Boleh kata macam tu lah. Kalau include friction, maksudnya dia akan ditolak daripada mg sin theta. Since mg sin theta, dia biasanya ke arah bawah. Mg sin theta di hadapan, friction di belakang. Betul. Okay. Lagi? Any other question?